Okay, so for FRQ number 2, we have a particle that has a mass of 4 kilograms and it is moving along the x-axis. There is a force acting on the particle, and that force is represented by this graph over here. As you can see, the force will vary over the distance traveled. The velocity of the particle is also given to be 6 meters per second at x equals 0. Okay, so for part A, we are asked to find the particle speed at x equals 2 meters. Okay, so to do that, I'm going to have to write this statement. This statement is my kinetic energy initial is plus the work done from x equals 0 to x equals 2 by the force is going to be equal to my KE, my kinetic energy at x equals 2. Okay, now to the side, I'm going to define each of these terms. My KE and I is equal to 1/2 mv squared. That's the equation for KE. And this is VI, so 1/2 mvi squared. And now I can plug in my numbers. So 1/2, and then mass was given to be 4 kilograms. VI was given to be 6 meters per second. And squared. Plugging this into the calculator, we're gonna get 72 joules. Okay, now for work from x equals 0 to 2. The work of x equals 0 to 2 can be found by integrating the force done from x equals 0 to x equals 2. So this is going to be equal to the integral of from 0 to 2 of f of x dx. Now to find this, we're essentially taking the area that is between the graph or the line and the x-axis. So from 0 to 2, we have an area of 10, or 2 times -5, 2 in the x and 5 down, so 2 times -5. 2 times -5, and that equals -10 joules. Okay, now for KE at x equals 2. KE at x equals 2. That is going to be equal to 1/2 times m times v at x equals 2, which is what we're trying to find, squared. And then we can plug in our numbers. So 1/2 mass is 4 kg. V at x equals 2 is what we're trying to find. And so this reduces down to 2 times v at x equals 2 squared. Okay, now I can substitute all of this into my original equation. So this KEI is 72 joules. Work that is being done is -10 joules. And my KE at x equals 2 is 2 times V at x equals 2 squared. Okay, so I want to solve for V at x equals 2, so I'm going to divide 2 over here. So 72 minus 10 divided by 2. That leaves me with V at x equals 2 squared on this side. Now I'm going to take the square root on both sides, so my V at x equals 2 is going to be equal to square root of 72 minus 10 divided by 2, and that is going to be equal to 5.568 meters per second. Now the question asks for speed, so all we have to do is absolute value this. So s at x equals 2 is going to be absolute value of vx equals 2 at this time. It's essentially going to still be positive, so this is still our answer. So that is our speed at x equals 2 meters. Part B asks us to find the time travel from x equals 2 to, x equals 0 to x equals 2 meters. Okay, so to do that, I'm going to use impulse equations. So impulse is going to be equal to the average force times time, and that's also going to be equal to the change in momentum, which is what impulse is. And the change in momentum is mvf minus mvi. Okay, so our average force from 0 to 2 is -5, as this is a straight line at -5. So -5 newtons is our average force. T is what we're trying to solve for. Mass is 4 kilograms. VF, this VF is our V at x equals 2, and this is 5.568 meters per second. Our mass is 4 kilograms, and our VI was 6 meters per second. 6 meters per second. Now we want to isolate for time, or actually I'm going to reduce this first. So -5t is this side, and this whole side reduces down to -1.729. If I want to solve for t, I'm going to divide -5 to this side, and so my t is going to be equal to 0.346 seconds. So that's how much time it's going to take for the particle to travel from x equals 0 to x equals 2. Part C asks us to find the impulse experienced by the particle between x equals 2 and x equals 4 meters. Okay, so to do that, I need to find my velocity at x equals 4 first before I can use my impulse equation. So again, I'm going to do this similar statement to the one in part A. So my KEI plus the work done by the force from x equals 0 to x equals 4 is going to be equal to my KE at x equals 4. Now, I've already defined KEI for here, up here 72 joules. I'm going to define the other ones. Work from x equals 0 to 4 and KE x equals 4. So work from x equals 0 to 4 is going to be equal to the integral of from 0 to 4 of f of x dx. Now again, taking an integral is the same as taking the area under the curve, and from 0 to 4, this is the area right here. Basically, this region, this whole thing. To do that, it's basically a trapezoid with a base of 4 and 3, and the height is -5. So area of this trapezoid is, so the average of the base times the height, so -5, and this gets me -17.5 joules. Okay, now KE at x equals 4 is going to be equal to 1/2 times m times v at x equals 4 squared. I'm going to plug in my numbers, or what I have, which is 1/2, and then m is 4 kilograms. V at x equals 4 is what we're trying to solve for. And so this reduces down to 2 times v at x equals 4 squared. Okay, so I'm going to plug in what I know into each equation. So KEI I found in part A is 72 joules. Work from x equals 0 to 4 is negative 17.5. My KE at x equals 4 is 2 times v at x equals 4 squared. Okay, so solving for v at x equals 4, I'm going to divide 2 first. So this side leaves me v at x equals 4 squared. Now I'm going to square root both sides. So v at x equals 4 is going to be equal to 72 minus 17.5 divided by 2. And then that's the square root of all of that. And this gets me 5.220 meters per second. So that is my velocity at x equals 4. Now I can set my impulse equation. So impulse is going to be equal to the change in momentum, which is mvf minus mvi. Okay. Now this vf represents v at x equals 4. Vi represents v at x equals 2. Because we want to find the impulse from x equals 2 to 4. So plugging in my numbers, 4 kilograms times what we just found right here for v at x equals 4 minus 4 kilograms times v at x equals 2 we found up here to be 5.568 meters per second. And plugging this whole thing in the calculator, we're going to get negative 1.390 kilograms, or our units is kilograms times meters divided by seconds. So that is our impulse. Part D asks us to find impulse experienced by the particle from x equals 0, x equals 3, and x equals 5. So this is fairly easy. I know it's going to be 0, and I'll show you why. Okay, so the work done from x equals 3 to x equals 5 is going to be equal to the integral from 3 to 5 of fx dx, alright? And this is the same as taking the area under the curve again. Okay, so if we take the area, it's going to be this and this. And since this one's negative and this one's positive and they cancel each other out, we know that the work done is going to be equal to 0. So this is one triangle, and this is the triangle above right here. So what I just did here was this represents the area of this triangle, and this represents the area of this triangle, and they're going to cancel out. So leaving this with 0 work, or 0 joules. Since the net work is 0, so here's my reasoning. 0 net work means that there is no change in velocity, and no change in velocity means there is no change in momentum, and no change in momentum by definition means that impulse is equal to 0. There we go. Part E asks us to find the particle speed at x equals 10 meters. Looking at this graph, I'm going to assume that the force remains constant at 5 newtons from so on, since there's a dashed line. So I'm just going to write down my assumption. So once again, I'm going to do the same thing as I did before for A and C when using KE to find my velocity. So my KEI plus the work done from x equals 0 to x equals 10 is going to be equal to my KE at x equals 10. Now I'm going to find work and KE at x equals 10 to the side, because I already have my KEI from other parts. So work from x equals 10 and 0 to 10 is going to be equal to the integral of from 0 to 10 of f of x dx. Okay, so taking a look at this, we have two trapezoids right here. So, and I know they're gonna cancel out, but I'm going to write on their areas anyways. And we also have a little part of section over here. Okay, so the two trapezoids area is, the first one is, the average is 4 plus 3 divided by 2 times -5. So basically the average of the base, which is 4 and 3, times the height, which is -5. And then same thing for the other one, so but then the height is positive, so plus 4 plus 3 divided by 2 times 5. And I also have a little section over here that is a rectangle. So I know that from 8 to 10 is the distance of 2, and 5 goes up, so my area will be plus 5 times 2. And ultimately this gets me 10 joules as my work from 0 to 10, because these two cancel out, and 5 times 2 is 10 joules. For KE at x equals 10, that's going to be similar to other ones, so 1/2 times m times v at x equals 10 squared. That's going to be equal to, plugging in my numbers, 1/2 4 kg times v at x equals 10 squared. This reduces down to 2 times v at x equals 10 squared. Okay, now I'm gonna plug in everything I got. So KEI, again, a reminder, is 72 joules from previous part up here. Work from x equals 0 to 10 is 10 joules, so minus plus 10 joules. KE at x equals 10 is 2 times v at x equals 10 squared. To solve for v at x equals 10 squared, I'm going to, just v at x equals 10, I'm going to divide 2 first. So 72 plus 10 divided by 2 on this side, and that's going to leave v at x equals 10 squared on this side. And I square root everything. V at x equals 10 is going to be equal to square root of 72 plus 10 divided by 2. And that's going to get me 6.403 meters per second. Now it asks for speed. So once again, I'm going to absolute value my v at x equals 10. So speed at x equals 10 is going to be equal to the absolute value of this. This is still positive, so my answer remains to be the same. Okay. Part F asks us if the particle does turn around at some point and head back to the origin and explain clearly. Okay. So my answer is that the particle does not turn around. Does not turn around and head back to the origin, because at all times and positions, my v is always positive. This is proven by the fact that at x equals 4, this is the point when f of x stops being negative. Meaning this is where v is the lowest. V is still positive at this point, even though it is the lowest. V is still positive. So if the lowest is still positive, that means everything else should be positive. So that proves that everything is positive. Every v is positive. Okay, so since v never changes signs, it never turns at any point to head back to the origin. Okay, so I just saw the announcement that there was a typo on part G of number 2, so I'm going to make a correction right now. So for part G, we're supposed to repeat part F instead of part D if v is equal to 2 meters per second at x equals 0. Does the particle turn and head back to the origin at some point if that is the case? Okay, so if the velocity at x equals 0 is 2 meters per second, that means my KE at KE initial is 1/2 m times v at x equals 0 squared. Now I plug in my numbers. Mass is 4 kg. V is 2 meters per second and squared. That means my KEI is 8 joules. Now, from earlier work, from right here, I've already found that the work done from 0 to x equals 0 to x equals 4 is negative 17.5 joules. So obviously, my KE at x equals 4 in this case will be 8 joules. So basically the initial KEI plus the work done from 0 to 4 of or f of x dx, and I found this to be negative 17.5, this to be 8 joules up here. Essentially, this thing is going to be negative, meaning that the particle does turn around at some point. I have to go back to origin because it changes signs. So yes, the particle, this basically this is some negative number, does so the particle does turn around at some point to head back to the origin. Now, if I want to find exactly what that point is, I basically just have to set my KEI equal to my the work done. So basically, it should be somewhere between here, because it should be less than negative 10 joules of work. So it should be somewhere between 1 and 2. I'm not gonna do that.